All right, so bisectors and triangles. There are two types of bisectors. There are angle bisectors and there are perpendicular bisectors. We talked about this before. Angle bisectors exist with just plain old angles, but now we're drawing them actually in triangles. And same thing with perpendicular bisectors. Ordinarily, we could draw the perpendicular bisector of a segment, but since a triangle is made up of three segments, now we can draw the three perpendicular bisectors in a triangle. The first thing we're going to do is actually define them again, right, and sort of practice. Then I'm going to hand out rulers, and I'm going to have you actually practice drawing these things. Now, we could be very accurate about this. Like if I said to bisect an angle, I could give you a protractor and say, measure this angle, then cut it in half, mark the point that's half of it, and create the angle bisector, right? There's also something in geometry called constructions, where you use like a protractor, a compass and a straight edge, and you can actually geometrically construct an angle bisector. Or there's actually the paper folding method, where you can construct things by folding paper, find the halfway mark. But we are really just going to sketch them. So we're going to kind of not be as accurate as we could be, but it's going to be good enough. All right? Okay, so when three or more lines intersect at one point, they are said to be, the word there is concurrent. Right? We said con is like with or together, and current is like flow. So flowing together, three or more lines that flow together are said to be concurrent. The point at which they intersect is then called the point of concurrency. The perpendicular bisectors are all going to be coming together at one point, and that point is at the center of what we call the circumscribed circle. So there's another vocabulary word right there, circumscribed circle. And what that word means is that the circle goes through each vertex of the triangle. Now, you actually can have a circumscribed circle with, a pentagon, a square. Anything can have a circle circumscribed around it. It just means drawn around, circumscribed. I'm going to come back to these other questions that are here after we explore this a little bit further. But just right now, understand that circumscribed circle is the circle that goes through each vertex of the triangle. Okay, now I need a volunteer to come up here, sit in my chair, and play around on my computer a little bit with this investigation right here. Anybody want to come? I can do it. Come on up. All right, so I'm going to challenge Owen to use this circle tool. You guys see on my software here, I've got this circle tool. I'm going to click on that. And if you click anywhere with the circle tool and then just pull, right, click and let go, and then just pull, you're going to create a circle. The challenge is I want him to find a point so that when he creates the circle from that point, it is going to be the circumscribed circle of this triangle. Now see, I'm off because I could get this to go through one of the vertices, but close to the other vertice, but I'm kind of way off, right? So I'm going to come up here and undo that, and I'm going to try again. Nope. Okay, so I'm going to let you try. Go for it. Try to make the circumscribed circle of the triangle. You have to let go and pull, yeah. Did he do it? No. Click again and then undo, yeah. Close to two of them, but a little bit off. Now, if I make this triangle like, you know, that, now try. Maybe you'll get a little closer. Hard, right? Okay, thank you. That was a good demonstration. Yeah. You want to try? Yeah. Okay.
I think that's close enough.
Well, close enough to two of them, but look at how far off you are here.
Oh, we need to get all three?
All three! Nope, circumscribed about means it has to go through every vertex. Okay, so that's pretty close, right? Tricky. Ooh, that was really close. All right, good job.
It's the midpoint.
Good job. All right, so now watch. I'm going to cheat. You watching? This is set up so that if I click on here, it creates the perpendicular bisectors of the side. Now, it doesn't show the congruence marks and everything, but understand that this point, this line right here is the midpoint of this side. Right here is the midpoint. And this is a right angle, right? On this side, this line is at the midpoint and a right angle. Here, same thing, midpoint and right angle. So these are perpendicular bisectors. If I move this around, those are going to stay perpendicular bisectors, no matter what I do here, right? If I stop anywhere, this is still midpoint, right angle, midpoint, right angle, midpoint, right angle. So it's drawn and constructed so that it stays the same. Okay, now you see that the three perpendicular bisectors intersect at this one point right here? Watch this. Boom. Right? So, is it cheating? It's just math. It's not really cheating. It's math. If you find the one point where the three perpendicular bisectors intersect, you will find the point that is the center of that circumscribed circle every time. Okay? Now, the nature of a circle is that the center is the same distance from every point on the circle. That's literally the definition of circle. Okay? So therefore, if I were to construct segments from the center to each vertex, center to vertex, center to vertex of the triangle. What would be true about those three segments? If all three vertices are on the circle, then from the center of the circle, if you drew a segment to each vertex, what's true about those three segments? Jack? Yeah, they're congruent. They're the same distance. Each one is a radius of this circle. Center to edge. That make sense? Okay? So when you construct the perpendicular bisectors of a triangle, you get the point that is the center of the circumscribed circle. And that point is equidistant to the three vertices of the triangle. That's a mouthful, that sentence. Go home and tell when your mom and dad say, "What'd you learn today?" Say, "Well, I learned that when you construct the perpendicular bisectors of a triangle, you find the point that is equidistant to the three vertices of the triangle, and it's the center of the circumscribed circle." Ha ha ha! They'll give you extra dessert for that one. Did you understand what I said? All right, so let's look at it more carefully. So, what do you notice about the radius? Well, what they're asking here is that the radius can be drawn to each vertex, right? So, therefore, point P is the same distance from the three vertices. Now, that center point is called the circumcenter. Circumcenter is the center of the circumscribed circle. That's why it's called the circumcenter. So if you look again at this thing that we created here, let me undo a bunch of stuff. Okay, notice where this point is. If I move and change the size of this triangle, what's happening to that point? Jumps around a lot, right? All right, so I want you to try to recognize. Sometimes it's inside the triangle. Sometimes it's right on the triangle. And sometimes it jumps outside the triangle. When is it inside? When is it on? And when is it outside? What type of triangle? How does this triangle change, in other words? Yeah?
I think that when it's outside, it's obtuse.
Yep.
And when it's on the line, it's a right triangle. And when it's inside, it's acute.
That's correct. Okay, so when you have an acute triangle, all three angles are acute, then you have the circumcenter. It's going to be inside the triangle, right? If it's a right triangle, it's going to be right on the triangle. And when it's obtuse, that's what makes it jump outside. Which is why you get this circumscribed circle, because you have to get these big circles. If it's an obtuse triangle, you need a big circle so that it goes through all three vertices. All right, we're going to explore that a little bit more in a minute. But let's talk about angle bisectors. Angle bisectors we have down here an angle bisector discovery page here. Angle bisectors, when you draw all three angle bisectors, you end up with a point of concurrency that is the center of what we call an inscribed circle. Now, an inscribed circle is just barely brushes the sides of the triangle. It's got one point in each, in common with each side. So it's like it fills the space it has without going past. Biggest circle you possibly can get without going outside of the triangle. That's an inscribed circle. All right, does anybody want to come up and try to get me an inscribed circle here? Volunteers? No? All right, I'll do it. So if I try to guess, I put my point here, and I try to get an inscribed circle. Oh, didn't work. So I'm going to go back and go here. Oh, getting a little closer. This one is possibly a little bit easier than the other one. That's pretty good. Right, so that's an inscribed circle. Now, if you want to construct the angle bisectors to find that inscribed circle, you're just going to bisect each angle of the triangle and then see the one point where the angle bisectors intersect. And notice as I change the size of this triangle, is that point ever jumping outside of the triangle? No, that stays inside the whole time. That point is the center of the the inscribed circle. Boom. Okay. So again, if we were to draw the radii of this circle, this time is that point the same distance to each vertex? What if we had a running race and I put 3 people on this point right here, and I said, okay, you're in this triangle, one person run to this vertex, one person run to this vertex, and one person run to this vertex. On your mark, get set, go. Is that a fair race? No. Right? This person is not going to win this race. But we have a circle. So by nature of a circle, it's equidistant from the edge of the circle. So the fair race here would be, okay, this person run to this side of the triangle. This person run to this side of the triangle. And this person run to this side of the triangle. This point is the same distance to each side of the triangle. The point where that inscribed circle intersects the triangle. Now imagine that I want to run to that back wall, and I want to get there as fast as possible. I have to touch the wall. Should I run that way? Why not? Which way should I run? Everybody says run straight. Well, I was planning to run straight. I was planning to run straight that way. Is that going to get me the fastest? It's still straight. What do you mean by straight? I mean, we all know what you mean, but what's the word? The geometric word for the path I have to take to that wall. Nope. Adjacent means right next to. Perpendicular, right? I need to run on the perpendicular path to that wall. That's going to get me there the fastest. If I don't go perpendicular, then I'm going the long way. Okay, so in a diagram like this, where they show you the angle bisectors and the inscribed circle, this point is called the incenter. it is equal distance to the three sides. Sometimes they will show that distance with little right angles here. The right angles that are drawn there are to show that it is in fact the perpendicular path to that wall. It's showing you that it's the shortest distance from that point to that side. Sometimes it's confusing because they throw these right angles on there and then you think, oh, it's a perpendicular bisector or it's an altitude or something else. Nope, it's just showing you that that's the fastest distance. Okay? All right, so let's go back to the notes again. So the incenter, this point is called the incenter, is the center of the inscribed circle. And so it's the same distance from the three sides of the triangle. And this time, this point of concurrency is always inside the triangle. It doesn't jump around like the perpendicular bisectors did. It's always on the inside. And you can kind of think about that logically. I mean, if you're bisecting the angles, there's no way they're going to intersect on the outside. All of the angle bisectors come towards the middle of the triangle. So if you look at some of these practices here, in the figure at the right, at which point do the perpendicular bisectors meet? Well, this looks like a confusing diagram, but you need to break it down, right? Perpendicular bisectors. Well, there needs to be right angles and congruence marks. So if you find the perpendicular bisectors, tell me at what point do they intersect? What's the name of the point where they intersect? Anybody? Find the perpendicular bisectors. Where would they intersect? I'm not sure how well that's going to work. Where do they intersect? Can you find the perpendicular bisectors? We can see this side has congruence marks, which means point Z is a midpoint. And then there's a segment coming out of that midpoint at a right angle. So therefore, RZ is a perpendicular bisector. If we come to side AB, again, there's congruence marks, which tells us that point S is a midpoint. And there's a segment drawn from that midpoint at a right angle, so that makes that a perpendicular bisector. So therefore, SR is also a perpendicular bisector. So at what point do they intersect?
Is it like the vertex of angle CRC?
So it's just going to be point R.
Oh, I didn't know if it was like, oh yeah, because that's
Yep, just point R. So you're right, it is the vertex of that, but we could just use it as a point. All right, I'm actually going to skip over these because I think you'll feel better about it after you draw them yourself a little bit. So we're going to practice drawing them ourselves. So when you're drawing angle bisectors, I have a couple of tips. Because sometimes when we draw the angle bisector, we don't actually split the angle in half. It's like optically we aren't so good at it. So my advice is to put a little arc in the angle that you're trying to bisect. And just focus on that little arc. It's like you're looking at a little slice of pizza. And just focus on splitting that little slice of pizza in half. Somehow it's easier for our brains and our eyes to split something little in half like that. Then you can extend it out. And I'm going to give everybody a ruler so that you can draw straight lines. So same thing again for each angle. You want to kind of split that in half itself first, and then you can extend it with your ruler. Now keep in mind that you want to make sure your angles are marked congruent, but not all the same as each other. So then our last one is going to kind of look something like that. Remember that when you're done, all three should meet at one point. And since these are angle bisectors, that one point would be called the incenter. So when you're done, you can see the one point where they intersect. Again, mark your angles a little differently from each other so that you see the pairs that are congruent. And then the point where they intersect is right here. We could, at this point, actually draw the inscribed circle, right? Because we did angle bisectors, that point should be the center of the inscribed circle, should be the incenter. All right, so let's turn over and look at the perpendicular bisectors. They're probably a little bit trickier to draw. I have a tip for this too. First of all, remember, drawing the perpendicular bisectors, you are drawing a segment that goes through the midpoint at a right angle. So treat each of the sides as its own segment. So I'm going to start with AC. And I'm going to find the midpoint first. Don't forget to mark the diagram showing that that's intended to be a midpoint. Now, this is where I would use your ruler if I were you. Use your ruler. Watch me up here for a minute. Watch me. This is just a tip to help you, okay? If you take your ruler and you line it up with the side that you're trying to bisect, and you slide it until the corner of your ruler is touching the midpoint. This ruler is shaped like a perfect right angle. So if you just trace your ruler a little bit right there, it gives you a right angle. And you can mark it as a right angle. And then turn your ruler the long way and extend it. That will help you to get perfect right angles. Otherwise, if you're just eyeballing it, believe me, it doesn't turn out as well. So having a right angle to trace is helpful, but you got to make sure that it's lined up with the side that you're trying to bisect. Midpoint and then right angle. Do a little right angle first and then extend it. Again, mark the midpoint with congruences. Little right angle first and then extend it. If you've done this correctly, or at least, a little bit accurately, it should come together at approximately the same point. That point would be called the circumcenter. So go ahead and try that on the other triangles, remember what we said. If it's an acute triangle, you're expecting that point to be on the inside. If it's an obtuse triangle, you're expecting that point to be on the outside of the triangle, which is why that first one made sense. And honestly, the more obtuse it is, the further away from the triangle that point's going to be. All right, so if you look in your packet at the bottom of page 11, let's just look at number 3. I'm not going to do the whole thing out, but I want to show you what I was talking about before. Notice in this diagram, point Q is the point where some bisectors come together. It's the point of concurrency. Are they showing you angle bisectors here or perpendicular bisectors here? Number 11 at the bottom. Are those angle bisectors that meet at point Q, or are they perpendicular bisectors that meet at point Q? So it's tempting to say perpendicular because you see that right angle there, but that's what I was talking about. These are not perpendicular bisectors, because even though there's a right angle there, it's not bisecting that side, right? So it's not a perpendicular bisector. That is actually an angle bisector. See how the segment QK is cutting this angle in half? It's actually marked with congruence. And QL is cutting that angle in half. So the point Q is actually a incenter. It's where the angle bisectors intersect. Angle bisectors intersect at point Q, which makes that the center of the inscribed circle. In other words, Q is the same distance to every side of the triangle. So those right angle marks that they're showing you is what I was talking about before, right? It's showing you that that's the shortest path from Q to side KL. And QO is the shortest path in that direction. And QM is the shortest path in that direction. So when they say to you, QN is 36, 5x plus 36, and QM is 2x plus 51, well, since they both have Q in common, they're both radii of this circle. Therefore, you can just say 5x plus 36 equals 2x plus 51 and solve from there. Okay, but I'm going to move us on to the next page. This is kind of a summary here. Perpendicular bisectors are concurrent at the center of the circumscribed circle. And so that point is equidistant from the 3 vertices. So here's the summary. If you want to find a point that is the same distance, equidistant, from 3 locations, the best thing to do is construct the perpendicular bisectors to find that point that's the center of the circumscribed circle, because that will be equidistant from the 3 vertices. So I could say it this way. If you want to find the point that's equidistant to the vertices, you have to cut the sides in half, perpendicularly, right? But to find a point that is equidistant from the 3 sides, you have to cut the angles in half. So it's kind of opposite. If you're finding a point equidistant to the sides, cut the angles in half. If you're finding a point equidistant to the vertices, you have to cut the sides in half. Okay, so it's kind of opposite. But this is where we can do some application. So I actually want you to turn to page 14. We're going to do a couple of problems here. Because this is the type of question that they would ask as like an application question. There are 3 historic districts in Fairfield, shown in the map to the right. They are Greenfield Hill. You see how they have it pointing right here. We'll do it in red. Let's see a little better. The Old Post Road, which I never heard that called a district, but whatever, we'll call it that. Old Post Road District right there. And then Southport is right here. So they're marking these 3, approximate locations of the districts. They want to know of the point that would be equidistant from these 3 districts. So there's 3 locations. You want a point that's the same distance from all 3 locations. So the first thing you want to do is kind of connect those dots to make a triangle. Now, are we going to make the perpendicular bisectors or the angle bisectors here? We want a point that's the same distance to the 3 locations. So in other words, a point that's equidistant from the vertices of the triangle. Is that going to be perpendicular bisectors or angle bisectors? Nope, it's the other one. I know this is confusing. Think about it this way. If there's 3 locations, and you want a point that's equal distance to those 3 locations, you want the circumscribed circle, because you want your circle to go through those 3 locations. You want to be at the center of the circle where the radius touches all 3 vertices. Not the sides, but the vertices, right? So we need the circumscribed circle here. So we're going to construct the perpendicular bisectors. Anytime they're asking you to find a point that's the same distance from 3 actual locations, it's going to be the perpendicular bisectors. Okay, so if we do this, we do a midpoint and right angle, midpoint and right angle, midpoint and right angle. So with my class the other day, I figured out that puts us right about at Ludlow. Look at this. Can you guys find your street on here? I found my street. I think this perpendicular bisector stuff puts us, I think this is Ludlow right here. See this blank space? Don't you think this is like the Winton Park area right here, those 2 little streets? There's my street right there. I live right there. Can you find your street? So I'm pretty sure that Ludlow is right about where the circumcenter is of these, boom, right about there. So anytime they ask you, there's these 3 locations. This next one, there's a playoff game, and the 3 teams are Ridgefield, Shelton, and Fairfield. They want to find a location that's approximately the same distance from all 3. That sounds fair. So, again, are we going to construct angle bisectors or perpendicular bisectors? 3 locations again, so angle or perpendicular bisectors? Perpendicular, right. Right, perpendicular bisectors this time, right? Both of these are asking the same type of question. So, maybe turn to page 15. Another map, another 3 locations. Are these going to be angle bisectors or perpendicular bisectors? Same thing again. Perpendicular bisectors again, right? If there's 3 locations and you're trying to find the equidistance. This was me going on vacation with my friends and we were trying to find a place equidistant. Okay, but let's look at number 4. This is a little bit harder to come up with a real life scenario for, so bear with me on this one. The owner of this triangular pool. This was a Google image, so somebody actually does have a triangular pool. That, unless it's photoshopped, I don't know. They want to put a fountain in the middle of this pool. Why? I don't know, but they do. Okay, and they want it to be equidistant from each side of the pool. If the diagram below represents the pool dimensions, mark where the fountain should be located. So here's the pool. If we want a fountain in the middle of the pool so that the fountain sprays around a circle equally around inside the pool, do we want an inscribed circle or a circumscribed circle? Inscribed. So should we make perpendicular bisectors or angle bisectors? Angle bisectors, correct. So for ones like this, where you're trying to squish something inside a triangle, not finding the location of three places, but just squishing something inside, this is going to be angle bisectors. So when you do the angle bisectors, you get the one point where they intersect. That's where your fountain should be. If you want it the same distance from each side of the pool. Okay, so just as a recap, angle bisectors meet at one point. That point is called the incenter. This is angle bisectors. The point is called the incenter. The circle is inscribed. Bless you. Notice these all begin with a vowel, in case that helps you, right? Angle bisectors, incenter, inscribed, circle. And then think logically about what an inscribed circle does. It touches just the edges, so this is equidistant to the sides. Not to the vertices, but to the sides, right? Same distance to the sides. So you cut the angles in half, you get the same distance to the sides. If we do perpendicular bisectors, the center is called the circumcenter. It's the circumscribed circle. And since it goes through each vertex, right, it's the same distance to each vertex. If we spelled this out perpendicular, right, this starts with a consonant, and that starts with a consonant, so that could help you. Okay, your homework is to do pages, is this page 15? This is 15, right? Yeah. Pages 15, 16, and 17. 15, 16, and 17 in your packet. All right? Okay. Good job.